Morning, everyone. On your days off, I am hoping that you will finish the ALEKS, including the cotangent, tangent, cosecant, and secant, and also work on the damped functions. So I know if you go online to the Larson Precalculus website, you will have those lessons and lectures under the Calc Chat and the Calc View. But I wanted to give you a quick overall of tangent, cotangent, cosecant, and secant, so you'll be able to do those activities on ALEKS. I'm also going to assign some bookwork to graph those functions, and you have the ones from the other day from sine and cosine, and I'm going to ask that you graph them, take a picture, and send it to me this week. So let's look at tangent. And if we look at our unit circle, remember tangent is y over x. So we look at our key points. We look at 0, pi over 2, pi, and 3 pi over 2, and then back to 2 pi, or 0. And y over x at 0 and at pi, it's 0 over 1 or 0 over negative 1. And as you continue around and around the unit circle, every multiple of pi is going to have a tangent of 0. So when we graph our tangent function, as I've done here on Desmos, notice at every value of pi, we have a 0. Now, what happens as we go beyond pi? Well, let's look at the other key points, pi over 2 and 3 pi over 2. Notice that tangent, again, is y over x, so 1 over 0 or negative 1 over 0 goes toward infinity. So here at pi over 2, negative pi over 2, and all odd multiples of pi over 2, we get an asymptote. So if I zoom out, you can see we never quite reach pi over 2, but we get close. We get that undefined. And then as you go in between 0 here on the unit circle and undefined, you get the values in between. And of course, they don't increase in a linear way, just like sine and cosine. You can take your calculator and go ahead and do 1/2 divided by square root of 3 over 2, square root of 2 over 2, which is 1, square root of 3 over 2, 1/2. You can take any other angle, and you can take actually sine over cosine and get the tangent value, and you'll be getting the tangent curve. Now, after this, all the other translations hold true, just like in every other function. So if I have y equals tangent x, and if I add a 2 to it, it just raises my graph up 2 units. If I add a negative 2 to it, it raises that same, or lowers that same graph down 2 units, just like it would on sine and cosine. If I put a value in front, say 5, it simply stretches my function. So it makes it look more linear. It'll have a curve to it, but the curve will get slighter and slighter, the larger and larger number. If you put something like 0.25, then it compresses it vertically. So I get a bigger curve to it. And you saw that same thing happen when we did our quadratic functions and our other power functions. As you had a coefficient that got to be more of a fraction, these values around 0 kind of hung close to 0. They became more square. If we take a number inside and we do 4, well, let's look at the period of tangent. The period is not 2 pi. Remember, the period is how often does one cycle repeat? Well, here's one cycle. It's just one of these tangent curves, and it goes from negative pi over 2 to pi over 2, which is a period of pi. So tangent is different in that it is a period of pi and not 2 pi. So when I put a number in front, that tells me how many tangent curves I can fit in one of those periods, or how many tangent curves I can fit into pi. So if I put a 2 there, that means I can fit twice as many tangent curves. If I put a 3, I can fit 3 times as many. If I put a 4, I can fit 4 times as many. And then remember the reverse. If you're looking for the period for one of these cycles of tangent 4x, that's just pi divided by 4, because the 4 tells us 4 fit within width of pi. So if you take pi, you divide it by 4, you get the period for one cycle. And of course, if you do a phase shift, it is simply, let's take negative pi over 4. I have simply shifted my graph to the right, pi over 4 units. You know, if you want to go left, then you make it positive. And those are all the same translations that you learned with sine, cosine. The same work for tangent. Now if we do cotangent, what's cotangent? Cotangent is the reverse. Tangent is y over x. Cotangent is x over y. So it's the same thing. It's just the inverse. And of course, look here where it's going to cross. If cotangent is x over y, it's going to be undefined now at 0, pi, and all the multiples of pi. So that's where your asymptotes are going to be. Let's erase this one so we can see it clearly. So here's my asymptote at negative pi, at 0, at pi. And since cotangent is x over y, my values at pi over 2, 3 pi over 2, and all the odd multiples of pi over 2 are going to be 0 over 1 or negative 1, which means 0. And so that's why it crosses at all the pi's over 2. So same thing with cotangent. It just shifts a little bit at where it crosses the x-axis, and then you can see the direction of the curve is the reflection of the tangent. All right, next step. Let's look back at sine. Sine of x. We know sine of x crosses at 0, 0, at 2 pi, at pi, and at pi over 2 it's 1, and at 3 pi over 2 it is negative 1. This all corresponds to our unit circle, and remember sine is our y value. So 0, 1, 0, negative 1, 0, and it rotates in between with all the other y values. What happens if we have cosecant, which is simply 1 over sine? Well, what we're doing is we're taking the inverse of the values we had before. So I know sine of 0 is 0. So the cosecant of 0 would be 1 over 0, which is going to be an undefined term. So we're going to, if I zoom out, you can see the asymptote. We're going to have an asymptote. And at every point on the sine curve where it crosses the x-axis, we know that the value of sine of x is 0, so the value of cosecant of x is 1 over 0, which is an asymptote. So we have an asymptote at each of our pi values for sine. Now, what happens at the pi over 2 values? We know the value of sine is 1, and the value of cosecant is 1 over sine, so 1 over 1 is 1. And at 3 pi over 2, 1 over negative 1, or 1 over negative 1 is negative 1. So our graphs of cosecant and sine are going to touch at these points because they're going to be the same point. And then all the values in between are just the reciprocal. So the numbers that are very, very close to 0 are going to be very, very close to infinity. And the numbers that are very, very close to this point, pi over 2, 1, are also going to be very close on the opposite side. So if we take the sine of x away, here's our cosecant function. And our cosecant function follows, again, all the other same rules and translations. If I want to move it up some units, oh, 7's too many, we can't really see it. If I want to move up 2 units, I add 2. If I add a negative 2, I shift the whole thing down 2 units. Look at the line that's in the middle now. It's y equals negative 2. I go up 1 unit to my first point, down 1 unit to my next point. If I put a value in the front, say 5, it just multiplies each value by 5. So here we go. So that changes my amplitude. If I want to change the period, I simply put a value in front of the x. So if I, right now, look at my period is not pi because pi only takes me one curve up. My period is now back to 2 pi because the period of sine is 2 pi. And one cycle includes one up curve and one down curve. Well, what if I want to fit twice as many in there? I put a 2. Now I have up, down, up, down. What if I want to do 3 times as many? I put a 3. Up, down, up, down, up, down. And now remember, when you want to calculate period, I know the normal period for sine is 2 pi. So 2 pi divided by 3 gives me the width of one period. And if you look, between 0 and 2 pi divided by 3 gives me right here one cycle, one period. Also, you can do a phase shift. Remember to put in your parentheses. So if I'm going to move it to the right, pi over 4, now everything is shifted to the right, pi over 4. So everything else holds. Once you get those shifts down, up, down, left, right, and horizontal or vertical, shrink or stretch, the same thing holds for each trig function. So the last trig function we're going to look at is cosine. So here's cosine of x, and we know that cosine of x is my x value. So at 0 it starts at 1, at pi over 2 it's 0, at pi it is -1, at 3 pi over 2 it is 0, and at 2 pi, or back at pi, it is 1 again, and that repeats. What is the inverse of cosine? Secant. So secant is the same idea as cosecant, only it's shifted. Just like sine is the same idea as cosine, only it's shifted by pi over 2 units. So when I'm looking at secant, I'm looking at 1 over cosine. Well, if cosine has a 0 value at pi over 2 and 3 pi over 2 and all the odd values of pi over 2, the 0 now becomes an asymptote because 1 over cosine, which is secant, is now undefined. So you're going to have all your asymptotes at your odd values of pi over 2. At all the values of pi's and their multiples, so 0, pi, 2 pi, 3 pi, negative pi, you either have a value of 1 or you have a value of -1. And since secant is 1 over cosine, 1 divided by 1 is 1. 1 divided by -1 is -1. And then all the values in between are the reverse. So those close to 0 now be close to infinity. Those close to 0, 1 or 2 pi 1 now are equally as close, but just on the other side of that line, y equals 1. And if we take off cosine, all the other same translations hold. You can shift it to the right or the left. So I'm going to shift it this time pi over 3. You can increase the period. You can remember 3 means there are 3 cycles for our width of 0 to 2 pi. So our period would be 2 pi divided by 3. You can move it up or down if you would like. So if I add in -4, and you can change the width between here by simply multiplying by a number within. So let's double it. And that brings the width in between the curves twice as wide as it was before. If we put a 3, it's 3 units, which would make a total of 6 units, but 3 units from this middle line here of y equals -4 because we've gone down 4 units. So same translations hold for each secant and cosecant as sine and cosine. Honestly, I would not memorize secant and cosecant. Whenever I have to think through of secant and cosecant and graph it, I don't like to memorize things. The only thing I do have memorized is sine and cosine because you can derive everything from there. So if I ask you to graph cosecant, graph sine, and then from sine, you know how to get cosecant just by touching the curves at the peaks. Same thing with cosine. If I ask you to graph secant and you don't remember, graph cosine, then you can just graph secant by touching the curves to the peak, and then the asymptotes are at the zero. The last thing I want to touch on, and we did touch on this period F, but not period B, is your damped functions. So let's say we want to fit a sine curve, or it will work for any curve, but we'll just work with sine, inside another function. So let's take the linear function, y equals x, and we're also going to look at y equals negative x. What happens if I want to stretch the sine function so it touches the borders? So it bounces on the borders of this y equals x and y equals negative x. Well, think through the mathematics of what I really want to do. I want to turn this negative 1 into the same value it should be when we're looking at y equals negative x. I want to turn this 1 value into the same value it should be when we're talking y equals x. So I'm simply going to put this function x in front, and now all of a sudden my sine value fits within my lines y equals x and y equals negative x. We call that a damped function, and you can do it with any graph. You can do it with a square, and it's easier to see if you actually graph that square. So here is my parabola. Notice at each value of the parabola, in order to get the sine curve to touch it and bounce off of it, I just have to multiply it by sine. And those peak values are 1. So at pi over 2, my sine value is 1, so I just get the value y equals x squared. But at the other values of pi, pi over 4, pi over 6, I'm only going to get a portion of that x squared, and that's what makes the line go down and up. And if you want the other part, you would just graph it down like so. That's a little bit harder to see. Let's change it to the square root function. So here we go, and then I'm just going to graph the square root function. And here we go. This is our normal square root function, and I want to bounce the sine, use the sine curve to fill within, and I simply take sine of x and I multiply it by the square root function. Also works for cosine, so you can do cosine in there. And we call these damped functions. The one they use for you on ALEKS, and I don't know why they picked this one, but is the exponential function, so e to the x. And then they have e to the x sine. So basically you've just got sine bouncing off of e to the x. And I do think they have variations, so it's not all e to the x. It might be e to the x divided by 8, which actually gives a little bit nicer picture because e to the x is pretty steep. So there we go. Our damped function next to e to the x is simply the sine curve bouncing off the curve e to the 8x. Now what they ask you to do on ALEKS is actually find some of these values. And what you simply want to do is plug in, they actually give you a table in the values. They ask you to plug them in for e to the x, plug them in for sine, and then multiply them together. So sine of 0 we know is 0. E to the 0 over 8 is e to the 0, which is 1, which would give us 0. And every time we hit a pi value, we're going to hit 0. But every time we hit a pi over 2 value, notice at pi over 2, when we plug pi over 2 in for x, we have pi over 2 over 8. So what's that simplify? 4 pi. And then we would have sine of pi over 2, which is 1. So our new value is not 1, but it's e to the 4 pi. And that's what we get right here. And so at every value that is an odd number pi over 2, you would either get a positive value that corresponds to that e to that value over x, or you would get the negative value, and it would bounce in between each one. So those are the damped functions. Please email me if you have any questions on how to do any of these ALEKS problems. Send me a screenshot. I will send you an explanation back. Planning on everybody having these done by Sunday night. We will do another paper review version on Monday and not have the quiz until Tuesday. See you guys next week.